Alright, very good morning. Now let's welcome back to part 2 of our theory we'll be going through. So let's look at question 5. Okay, question 5. Three plotting compasses are placed close to a solenoid to carry a current. Remember, this is the method of actually plotting out our magnetic field lines. So before we actually proceed on, that reminds me, maybe we should do a quick recap in terms of how we would like to plot the magnetic field lines first. So can I get all of us to move to question? Question is this? This is section C, question 1C. Section C, question 1C. So let's run through actually how's the method to actually plot out the magnetic field lines. So the materials that we require will be a bar magnet, plotting of the compass, a plotting compass, and a plain paper. So what's the procedure? Place the plotting compass such that it touches one pole of the bar magnet. So this is where our just like us to actually copy this down so you have a reference for this. Place the plotting compass such that it touches one pole of a bar magnet. Mark the positions of the ends south and north on the compass needle using pencil dots 1 and 2. Next, shift the compass so that the south end of the compass needle is exactly over dot 2. So what you want to do now is you make it as close as possible towards the previous dot, the edge of the previous dot, so that you can try to draw a line later. Mark the new position of N using a third dot. Repeat step 2 until the plotting compass reaches another magnetic pole. Join the dots that have been plotted on the paper. This will give a field line of the magnetic field. Use steps 1 to 3 to plot other field lines on both sides of the magnet. So now this is the steps to actually draw out the magnetic field line around a compass. What is the next thing I want to highlight here is that it's also a very good practice in telling us how we would like to write an experimental procedure. So the first step here is so they write on the materials. So when you write down any experiments itself, tell them what are the materials that you will need to use. Next, you write down your procedure. In your procedure, you label the steps 1, 2, 3, 4, 5 very clearly. Next, you tell them what they are supposed to do. You have to be very clear and explicit. Like example, you want to mark the positions of S and N on the compass using pencil dots 1 and 2. So you got to be very specific. And then when you need to repeat all these steps again, you say repeat step 2. So it's very clear. You need to do step 2 again until you reaches another pole. And if you need to do any other things again, you just say use step 1 to 3. So this is a good example of writing out the procedures very clearly. Okay, so let's go back to our question 5. All right, so for question 5, they are plotting out the magnetic field lines. How many compass needle will not change direction if the current through the solenoid is reversed? So now the current is reversed. So if the current is reversed, the direction of the magnetic field will also flip to the other side. Okay, so let's take a look. How many compass needle will not change direction if the current through the solenoid is changed? So what we have here now, let's also recap how we can actually identify the north and south pole in this kind of solenoid. So this is a solenoid where there's a coil of wire. We can use our right hand. Okay, we can use our right hand itself. Your fingers will be the current that is flowing. So how does the current flow? The current flows here, 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 here. So what you want to do is you want to curl up your right hand. Okay, so this is your thumb. So this is your thumb. This is your fingers. Okay, this is your right hand. So your fingers will follow the current. This, so it goes upwards. Okay, and your thumb will point in the direction that which part is north. So in this case, north will be here because when you use your right hand grip rule, points that there is north and this is south. So what happens now if your current were to be reversed? If your current to be reversed, what will happen is everything will flip. Okay, everything will flip. Now your current will go in the other direction. So now your current will go down. And now instead of it being north, now it will be south. Instead of being south, this is north. So what will happen to all the direction of the magnetic field? They all will have to change direction. So all of them will change direction. How many will not? Answer is 0. Okay, because all of them has to change direction. Okay, question 6. Plotting compass 1 and 2 are placed within the magnetic field. So 1 is here. 2 is here. Which of the following shows the direction of the two compass? So magnetic field lines always flow from north to south, north to south. So in this case, all will go out here. This one will go out, symmetrical, okay? And if we draw the lines here, we realize that it should go this way, it should go this way. Okay, so which of the following shows the compass? Neither. They are all in the same direction as you can see, so they should be following A. Okay, so that is how we identify the direction of the magnetic field lines. Okay, let's move on to section B, question 2. A magnet is used in an experiment to identify which of two metal specimens A or B are iron or steel. So remember, iron is a soft magnetic material, whereas steel is a hard magnetic material. The south poles of the bar magnet are used to attract metal specimens A and B. The other end of the specimen are then used to attract the soft iron tags, so also made of iron. Figure 20.3 and 20.4 show the different degrees to which the metal specimen continue to attract after the bar are removed. So after the bar is removed, this is what will happen to each of them separately. So identify A and B. The one that is able to attract more even when the magnet is still not there is a hard magnetic material, which is steel. So B is steel, A is iron. Still explain which metal is a hard magnetic material. Okay, as we explained, metal specimen B, why? It is less easily magnetized. As such, we can see it picks up fewer tags. You can see here, there are fewer as compared to here because it is very difficult to be magnetized. When the bar magnet is removed, metal specimen retains the magnetism. So remember, a hard magnetic material is very difficult to be magnetized. It's very difficult for it to demagnetize. Both are very difficult. As such, it will continue to hold more soft ion tags compared to A. Explain why the hard magnetic materials are commonly used to make strong permanent magnets, because they are able to retain their magnetism for a long time. Remember, we want this to be permanent. It must be able to retain for a very, very long time. Okay, so let's move on to section C. Now, section C, on the first part, question 1, I'll go through in a separate video. Question 2, let's do that first. So why we want to do this question here is because usually in your O-level itself, there are questions which give you a lot more information. You must be able to sieve out this information for use. Okay, so figure 20.12 shows a recording tape from a cassette. So this is a cassette used during my time. It's basically to record music. I think some of us at home you should may have if you check with your parents. To record this itself, you must put it into a tape recorder. In your tape recorder itself, an alternating current is passed. So the alternating current is here, AC. Will pass through the coil. So this is a coil. This is a solenoid. So remember, a solenoid itself is able to generate a magnetic field. This magnetic field will be able to generate a magnetic force. It will cause the material inside of it to be magnetized, to become an electromagnet. So in this case here, this itself to be an electromagnet itself must be a soft magnetic material. Okay. Next, the tape is coated with a permanent magnetic material. So this is permanent. So if you want it to be permanent, you must have a hard magnetic material that becomes magnetized by the recording head. Okay. Explain how the tape becomes magnetized. The tape is magnetized by induction. So now we are looking at this tape here. How is it magnetized? It's magnetized by induction. Why? Because there is no contact, but we do know that there is a magnet. So in this case, this is a magnet. This whole thing here is a magnet. This magnet will induce in this tape here. So the tape is magnetized by induction as the recording head is an electromagnet. It has become an electromagnet. Okay. Figure 10.12 shows the section of the tape are magnetized in opposite directions. So asking you why is it some are facing one direction, the others are in another direction. So this has got to do with the AC current. Remember, the AC current is the one that changes direction also. So the current in the coil changes direction as the tape is passed under the recording head. The change in current direction will change the direction of the magnetic field of the recording head. As such, this will cause the direction. This will cause the tape sections of the tape to be magnetized in the opposite direction. So it's because of your AC current that caused this magnetic induction change. Okay. Still, the reason for the permanent coating of the permanent magnetic material is to ensure that information recorded on the tape is not easily changed by any external magnetic source. So we want it to be permanent. Anything from outside, we do not want it to destroy the information. So last time we used this cassette to store the boy band, or last time no K-pop, J-pop, or from the American boy band, Backstreet Boys or whatsoever. Okay, let's look at part B. 3 specimen materials are tested using the apparatus. Test is to assess if they are suitable materials for making the recording head. So you want to use this material here, this one here. So what material should they use? So remember, we have identified that we want it to be a soft magnetic material. So what does soft magnetic material means? It means that the number of needles it pick up must be a lot, and the number that's left on the specimen after the circuit is open must also be, number of needles left is very little. So it must be able to pick up lots. It must be able to retain very little when the circuit is open. Okay, so which of these few? Yes, B. So the other two is telling you that they are hard material, and C is a bit harder as compared to specimen A. Stay and explain which specimen is more suitable for making the recording head. B is more suitable. Why? Because it's a soft magnetic material, easy to magnetize and demagnetize. Why do we want to get a soft magnetic material that is easy to magnetize and demagnetize? So that it can respond quickly and effectively to changes in the direction of the alternating current to magnetized tape. Imagine if your magnetic head itself responds very slowly. Your recording tape will not be able to record any music because your music will all just be one tone. Okay, so we want it to be able to change very, very frequently. Say a problem that might arise if the current supplied by the battery is weak. So I'm trying to tell you that now here, this battery, if the current inside here, wrong direction, it always flows on positive. So if the current inside here is very weak, what will happen? Remember, current must flow before there'll be a magnetic field, before there's a magnetic force, before we can induce before we can form an electromagnet onto the specimen. So the specimen can become an electromagnet. So in this case, when the current flowing is weak, the magnetic force created will also be weak. This will reduce the number of needles picked up. And how does this affect? Remember, you got to answer back your question. The results will be less conclusive, or you will not be able to get accurate results. Okay? So we will refer to the drawing of the few lines in another video.